So, second speaker today is Afonso Bandeira. And, well, I said there are two classes of speakers here. He sort of falls between the two classes because I've known him for some time and first met him at an event in his home country, Portugal, for undergrad students, which was obviously a while ago since he's now finishing his PhD in applied math at Princeton. And he's got some very interesting results. We'll be talking about one of them today, about random matrices with independent entries.
Right. Thanks, Roberto, and thanks so much for the invitation. It's a real pleasure to be here. Okay, so I'm going to talk today about, well, this is the title of the talk, and the paper is a bit long, but I'm interested in understanding the spectral norm of the matrices with independent entries. And all of that I'm going to talk about is joint work with Ramon van Handel. Okay, so let's say, to start with, that we're interested in understanding the spectral norm, the expected spectral norm of a random matrix with Gaussian entries, and they're all independent. So let's define the model. Let B be an Rn matrix. Let's say that it's symmetric. And let's denote its entries by little bij's. And I want them to be positive or non-negative. And the random matrix I'm interested in is a matrix X that is also symmetric and whose ij entry is equal to bij, gij, where the gij's are IID standard Gaussians. Okay, and it's symmetric, so gij is the same as gji. Okay. And so the question that I'll be trying to solve, or what both today's talk and the one on Thursday is going to be about, is trying to understand what is the expected norm of the spectral norm, the expected value of the spectral norm of X. Okay, and by spectral norm I mean the largest eigenvalue in absolute value. Okay. So by this I mean the maximum over all little x of norm 1, little x transpose x. Okay, and big X is symmetric. Okay, so to gain a little bit of intuition, let me first start with a few simple examples. And please, if anything is not clear, interrupt, ask questions. So a very, very simple example is when all the bij's are equal to 1. Sorry? Oh, right. True. Thank you. So when all the bij's are equal to 1, okay, then X is a Wigner matrix. Okay, it's just a matrix n by n with where all the entries are independent, IID Gaussian 0, 1, and we know the answer in this case. The answer is 2 times square root n plus some little o of that. Okay. On the other hand, so let's look at another example. Let's say that bij is equal to the Kronecker of ij. So the delta ij, meaning that bii is 1 and bij is 0 if I is different than j. Okay, so it's just a matrix where on each diagonal element you put a Gaussian. Then the spectral norm of this, right? So if you have a diagonal matrix, then the spectral norm is just the maximum of the diagonal entries. So this is just the maximum over all i's of the absolute value of gii. And there's n of them, so this looks like square root of 2 log n. Okay? So we want to capture these examples and many, many others. Okay, so let me talk a little bit about what is known. Okay, so one parameter that's very important is the following. So, okay. So the spectral norm of X, the expected value of the spectral norm of X is the expected value of this definition of spectral norm, so the max right? If I switch the expectation with the max, I can only get smaller. Let me do the square just to make just to avoid complications in calculations. Okay, so. Let me do this. Yes, let me do this. The matrix is symmetric. Let me do this here. I just want to avoid any issue. Okay. Okay. And therefore, I don't even need any absolute value. Okay. And so if you compute this is the same now as the max. So what this is equal simply to the spectral norm of X squared. And I'm going to call this sigma square. Okay, so let's see what it is in this case. Okay, so what is X squared? So X squared goes, right, think of what X is a matrix with independent entries. So essentially, X squared, what it has is, and it's symmetric, so it just has inner products between columns and rows, or inner products between rows, say. And the rows are independent, so all it's going to pick up is things in the diagonal. Right? So this is simply a diagonal matrix, meaning that the expected value of X squared is simply a diagonal matrix where on this diagonal entry, we'll just have the sum over all j from 1 to n of b1 j squared. Right? Because this will just be the expected L2 norm of the row 1, and then of the row 2, and so on, and all the other terms outside go away. And so this means in particular that this is just the largest diagonal element, and so sigma square is simply the max over all I of some ij bij squared. Sum over j of bij squared. Okay. And so, in particular, we know for sure that the expected value of x needs to be smaller than sigma. Needs to be bigger than sigma, sorry. Okay. So we would love if it was actually sigma, but this turns out that it's not the case always. So what is known in this regard? So there's a now old result. It's called non-commutative Kinchin. So it applies in a much more general setting, but in particular in this setting it says the following. So what non-commutative Kinchin, and this is by Picard and Vizier. It's from like late 80s. And it says essentially that expectation of x smaller or equal than square root log n times sigma. No? But it gives this. Okay, so I was going to say also that there's another way of getting this. Okay, so there is some later papers improving the constant, and you need those in. I see. Okay. So it's by Agar, something like this. I see. Okay. So there's another approach of getting this, which is based on matrix concentration. This there's a few people that have done work on this. Sort of started with Ashford Winter, and then two people in the room contributed a lot to it, Oliveira and Trapp. And so, okay, after you have this later results, but essentially in the end you get something like that. And it applies in a much more general setting. And so it means that this observation of the fact that it needs to be bigger than sigma essentially is, it also needs to be smaller or equal than sigma times the square root log n. So what we want to understand is when, right, if this is tight or not. And so on the other hand, there's another result that also applies to a much larger set of examples, which is due to Gordon. And this is essentially a net argument. And what it's doing is comparing. One way of thinking about it is what would happen if you compare with the Wigner matrix. So each entry, think of Bij as a certain Bij. If all the entries had the value of the largest Bij, then it would be a Wigner matrix. And sort of the spectral norm, at least intuitively, could only be bigger. So what the result says is that the expected spectral norm of X is smaller or equal, this is all up to constant, than the max entry times square root n, right? Which would be what you would get for bigness. Okay, and essentially you can think also of this as a net argument, right? If you do an epsilon net over all directions, you would get something of this type. Okay, and now I'm going to call the max of Bij sigma star, just because I'm going to be using it a lot. Okay, so these two results, they apply to a much larger set of examples, but there are also other results that are specific to this case, and I'm going to show them now. So there's one by, okay, so perhaps the first one is by Latala. It's in 05. And Latala showed that the expected value of X is always smaller or equal than sigma, plus a term that depends on the Bij's, and it's essentially the 4 norm of all the Bij's. So sum ij, Bij to the 4, 1, 4. Okay. There's also one by Riemer and Schut. In 13, that so what it says essentially is that this is smaller or equal than log of something here that I'll describe. So let me call this n tilde sigma, where n tilde is some sort of intrinsic dimension. So what n tilde is something like this. So the 1 norm of all the B's, so think of the matrix of all a vector made of all the B's, and the 1 norm of that over the infinity norm. Okay, so it's the 1 norm of the B's divided by this parameter. But if the B's are more or less homogeneous, this is n, essentially. And so this result in most instances, what it says is log n to the 3/2 times sigma, and it's dominated by non-commutative Kinchin. But it does have a more, so if the Bij's are very unhomogeneous, or if it's a matrix of smaller dimensions embedded in large dimensions, it does give an improvement. And there is yet another result by Seninger. This, I think, is from 2000. That is for another slightly different setting. So if instead of Gaussians I have Rademacher random variables, so if my xij now is equal to epsilon ij bij, where epsilon ij are Rademacher random variables, so they're -1 with probability 1/2, 1 with probability 1/2. Then he showed an improvement over non-commutative Kinchin, and it's sort of a mysterious thing. I'll explain later the intuition. And he gets log to the 1/4. So now let's look at the examples, right? The two examples that we have. Okay, so we have Wigner. We have diagonal. Okay, and let's not think about Seneger because we're doing it for Gaussians. So I'm going to talk about this later. But so let's say you have Wigner and diagonal. We know what the answer is for each one of these cases. Here it should be square root n. Here it should be square root log n. Let's see what each one gives. So non-commutative Kinchin. Gordon. Okay, so non-commutative Kinchin for Wigner, right? So sigma is square root n. So non-commutative Kinchin for Wigner gives square root n times square root log n. For diagonal, it gives square root log n because in that case, sigma is 1. Gordon, on the other hand, here gives the right answer because sigma star is 1, the largest entry is 1. But he gives a terrible answer in this case, right? Because sigma star is again 1. Latala here gives, so sigma square root n plus the fourth norm of all the entries. So you get something like n squared to the 1/4. So you actually get something in the order of square root n. So you get again the right answer. But if you do the same thing here, you don't get the right answer. You get something like 1 plus n to the 1/4, right? Which is the wrong answer. Okay, so at least seems the known results for these two simple examples, they capture, the right answer is captured here and here and here, and we want a bound that captures the right answer everywhere, and not only in these two examples, but in many other examples for which all of these bounds fail. Okay. So I'm going to present the result now, and then I'll prove it on my other talk on Thursday. Okay, so the result that we have is the following. Going to worry about constants for now. Okay, so note that this captures exactly both examples, because in the case of Wigner, sigma star is 1, sigma is square root n, so you get the square root n, and in the case of diagonal, this is 1 and this is 1, so you get square root of log n. And it captures many other examples, and I'll talk a bit more about it on Thursday. And in particular, you can actually get nice constants, and you can get something like this. So for any epsilon bigger than 0, this means in particular that if you do Wigner, for example, where this is 1, you can pick epsilon going to 0, and you can recover exactly the 2 square root n. So not only it recovers the right behavior, it recovers the right behavior even on the constant. Okay, because I just need to pick epsilon little o of 1, sufficient so that this doesn't blow up too much, and I get exactly the 2 square root n. Okay. So one way of understanding this bound, so let me see what I should erase here. Okay, so one can show that sigma star is always smaller than sigma, and it can't be too small. So sigma over sigma star is bounded below by 1 and above by square root n. And so now if you grab that, so essentially non-commutative Kinchin and Gordon are the two extremes of these. So for if sigma over sigma star is equal to 1, then expected value of x by that bound is smaller or equal than, well, the sigma term doesn't matter because the sigma star is of the same size and it has a log n. Again, so this is non-commutative Kinchin. On the other hand, if sigma is much bigger than sigma star, then the term sigma is the only one that matters, and it's equal to sigma, but sigma is square root n sigma star, so, right? And you can prove these two results just by using each one of these inequalities for this particular case. Okay, so this is Gordon. So it's strictly better than any of the two in all the instances that we can cover. It doesn't cover Latalis. Latalis is not comparable since it doesn't have any dimension factor on it. Okay, so let me see. Okay, so I'll explain a bit more of the context of it, and then I'll wait for the proof for Thursday. Okay, so the natural question is, okay, so this bound is better than the others, but is it tight? Can we still improve it? And I would argue that it's essentially tight. So we know for a fact that that expectation of x is bigger than sigma. And so the term on the left needs to show up. On the other hand, if you think about it, that the expectation of x also needs to be bigger than the largest entry. So it needs to be bigger or equal than the expectation of the max over ij of bij gij. Okay? So as long as there are enough bij's, like a polynomial in n number of bij's, that are roughly of the same size, then right, as long as, say that the largest bij has some value, say 1, as long as there's a polynomial number of them that also have the same value, say 1 in each row or something, then this needs to be bigger or equal, right, in some condition. So if it's homogeneous. Times the largest Gaussian among all those entries, and this will be of size square root log n. Right? Because the largest Gaussian in absolute value among n Gaussians is of size square root log n. So this means that this should be bigger or equal than square root log n. Okay, so in particular, it needs to be bigger or equal than the term on the left, and then the term on the right, then the bound is tight, at least up to constant. Okay, on the other hand, you don't expect it to be always tight, because otherwise you'd be recovering things that are known to be difficult to understand. So one example is if I put a matrix that's like this. So I give a matrix, so let's say that this is the B, and I give the following matrix. 1 over square root, say log 2, and then the other entry here is 1 over square root log 3, and so on, all the way to 1 over square root log, say, n plus 1. Okay, then the spectral norm of this, if I put Gaussians on it, so now x will be the Gaussian 1, 1 times this, Gaussian 2, 2 times this, Gaussian n, n times this, say that 0 is here. And it's the largest among all the absolute values of all these numbers, and this is known to be constant, but it's not it's a bit unreasonable that we would and capture this kind of behavior from inequalities of this type. Right? So in particular, our inequality here would give, right, this is the largest entry, so it would give square root log n, but this should be constant, but it's sort of unreasonable that we would expect to capture things of this type. However, there's a conjecture that would indeed capture this kind of behavior. And okay, so Riemer and Schutt make this observation that I'm not sure they conjecture it, so I don't want to say that they do conjecture it, but they say that, so one obvious bound, so okay, one obvious bound is that the expectation of x needs to be smaller or equal than the expectation of the maximum over all i's okay, so the expectation of the spectral norm needs to be controlled by the expected largest L2 norm of the rows. Okay, and so they make the observation that they know no counterexample for the converse inequality to be true. So no counterexample is known for the following claim. Okay. So this would completely explain things of this type even. And it'd be completely tight because we know for sure that that the right-hand side is bigger than the left-hand side. And wait, what am I? This is obviously right. Right. So this is obviously bigger than that in general, but no counterexample is known of an instance on which the order of this is bigger than the order of that. So note that this would completely describe what's happening. And our result sort of shows why it would be difficult to come up with a counterexample for this. Because a counterexample for this would have to be super inhomogeneous. Would have to have some BIJs that are very big, and there'd be very few of them, and then all the other BIJs would need to be much, much smaller. And so this shows that, at least to come up with a counterexample of this, will be non-obvious. It will have to be a super inhomogeneous example. And so it'd be super interesting if something like this was true. But we don't know. Okay, so I'll explain another thing that the result implies, and then I'll explain how to prove it next time. Okay. So another thing that was known okay, so it was known that, so let's see, this is a theorem by okay, so quite a recent theorem. And it says, suppose that the BIJs are either 0 or 1. So they can only be 0 or 1. And there's exactly k of them being 1 for each row. So Bij fix I. Bij is 1 exactly k times. Exactly 4 kj's. Okay? So it corresponds to the adjacency matrix of a k-regular graph. Then they showed that if k is growing to infinity, but smaller than n, the size of the graph, so this is, again, n is the dimension of the matrices, then they showed that the empirical spectral distribution, so actually, of x when it's normalized right, so normalized by square root of k, then this converges in probability as k goes to infinity to the semicircular law. So this is a very nice result on all the minus 2. So, okay, so the semicircular law is just you go from -2 to 2. And it's the empirical distribution of a Wigner matrix, and essentially saying that if you have a matrix that has Gaussian entries on each row of on k entries, doesn't matter which k entries, but as long as it's exactly each row has k entries and it's symmetric, then the empirical distribution looks exactly like a Wigner matrix of size k. Okay, but this doesn't mean that the spectral norm also looks like it, right? Because just because it converges in probability, that doesn't mean that there's not a guy here. Right? It just means that most eigenvalues are here. And in particular, there was a conjecture of what happened with the spectral norm of x. And what was known by the same authors was that if k grew large enough, so if k over log to the n, log to the 4, log to the 9, sorry, log to the 9 of n went to infinity, then indeed the spectral norm over square root k converges to 2. So meaning that the largest eigenvalue really is here. There's nothing outside of the bulk. Okay? And that's also what happens for Wigner matrices, for example. And our result immediately gives, right, because essentially sigma is square root of k, because it's the L2 norm of a row. Right? There's exactly k1s and the rest is 0. And essentially, our result immediately gives the following phase transition. It says that, okay, so it says that if k over log n, so just one log, goes to infinity, then indeed x over square root k, so spectral norm of x over square root k goes to 2. On the other hand, if k over log n goes to 0, then there needs to be an eigenvalue in the outside of the bulk. And if, on the other hand, in the case in between, if k is in the same order of log n, all we know is that x over square root k is bounded. So it goes to some constant, but it may not be 2. So it may. To infinity, yes, of course. Yeah, thanks. Right, thank you. Yeah. Right, and so in particular, it will be very interesting to understand whether there is some constant for which if k is bigger than that constant times log n, it actually goes to 2. I mean, it's reasonable that something like that happens, and just we don't know. We just know what happens when k is over an order above log n, and it's completely open what happens in this regime. Mm-hmm.
So would it be reasonable to expect that perhaps the answer that third item is not to
Definitely, yes. Yes, very likely, yeah. But I feel like but even so, there might be a constant for which above that constant is okay for every graph. And even that we don't know. Right, okay. I still have quite a while. Let me talk about, let me explain the log to the 1/4 in Seininger's result. Okay, so I'll leave this here. Is there any question? That was. Yes. Yes, from this, so I can talk more about it on Thursday. But yes, after you have it for Gaussians, you can control it for mostly anything. right? I mean, it might be that the tail here now gets, if it's an heavy tail distribution, it might be that instead of log n, you log n to some power, depending on the size of the tails. But you can get things like matrix Softing or matrix Bernstein in this setting just out of this inequality by using the standard methods. And after you know the expected value, you can get the tail bounds just out of Gaussian concentration, and then the tail bounds you can change from, you can compare other stuff to Gaussian.
Is it also enough if you have finite moments? I mean, okay, then the log n will probably polynomial.
What do you mean?
I mean, basically, well, just finite force moments.
Mm-hmm.
So you could get something like that where you could get sigma, sigma star would be the largest set.
Yeah, something like this, right. Or something like the largest variance of each entry. The largest variance would be what would show up. If you want, I can describe it in detail on Thursday. But you can get the tail bounds that then you can use. As long as the entries are independent, you can get pretty sharp tail bounds. Anything, but this only applies for independent entries.
Yeah, I was just thinking about like just a finite moment and not like
Oh, I see. Then I have to think about it. Yeah. But if you have, say, an exponential distribution, then instead of a square root log n, you pick up just a log n. Right. But finite moments, yeah. I'm not sure. Okay, so let's now shift gears a little bit and look into the example of Rademacher random variables. Okay. So again, the matrix is Xij is epsilon ij bij, where epsilon ij is the Rademacher. So it's -1 with probability half and 1 with probability half. And now you can see that the bound is not necessarily tight anymore, right? Because let's say if I pick, for example, the diagonal matrix, it doesn't matter what signs get, what Rademacher I pick for the diagonal. It will basically be a diagonal matrix with plus or minus 1 in the diagonal at random, but the spectral norm of that will always be 1. So the result is not quite right in that setting. And in particular, the result that Seninger has that I showed already said that spectral norm of X is smaller or equal than log to the 1/4 times sigma. Okay. So sigma times log to the 1/4. Okay, and it's sort of mysterious why this log to the 1/4 is here. And then I'll show that we can actually recover it through our inequality. Okay? So we know that, well, the Rademacher bound, we can compare it to the Gaussian, so that will be true still. So next, we know that, so let's prove this with now that we have that, we can give a very simple proof for this theorem, which the original proof is not so simple. Okay, so we know this. On the other hand, we know for a fact that the expected norm of X needs for sure to be smaller or equal than the spectral norm of B. Right? It's just triangular inequality. The worst thing I can do is just put 1s everywhere. This will increase the spectral norm the most. You can just see that by triangular inequality. And so the expected value of X is smaller than B. Right? And this is usually how, this is a bit of how inequalities for when dealing with Rademacher random variables are improved, is by noting that, okay, there is some Gaussian bound, but there's also the fact that if I put 1s everywhere, this is the worst case, so I need always to be smaller than that. Okay, is that clear to everyone? Okay, so now we just do the following construction. So now we're going to basically interpolate between these two bounds, and we're going to recover this one. So we split X into X plus and X minus. And x plus are going to be the largest entries. So they're going to be the entries that are bigger, for which the b is bigger than u. So x plus ij is going to be given by the Rademacher, bij, and the indicator matrix of bij bigger than u. Right? And x minus are going to be the other entries. So j, bij, smaller or equal than u. Okay? And so now we're basically going to apply one bound on one of them and one bound on the other. Right? And you'll see that we recover, and then pick u in the right way. So in particular, we can use our inequality on so we can use our inequality on x minus. Okay, so if you use it on x minus, you get sigma plus, the largest entry is now u, because we're just picking the ones that are smaller than u. Right? On the other hand, okay, so we have this. On the other hand, just by Grishkorin circle theorem, okay, so first we're going to apply this. So this is for sure smaller than bij, u of bij bigger than u. Okay. And now, just by Grishkorin circle theorem, this needs to be smaller than the L1 norm of each of the largest row. So this needs to be smaller than the max over I of the sum over j of bij and okay, so all I did was using Grishkorin. And now I want to make this in a way that the sigma starts showing up. So how do I do that? I can just multiply bij on each entry. So max of I, sum of j, and then I can make bij square. And everything that I multiplied was bigger than u. So I get to divide by u, and I'm still bigger. Right? Because there was just one before, I made it square. Every entry I multiplied by bij, all the bij's are bigger than u, so I get to divide by u. Okay, so now what is this? This is for sure smaller or equal than sigma square over u. Okay, so this means that the spectral norm of x is smaller or equal than the sum of the two, so sigma plus u square root log n okay, and it's clear to see why this is the case. You just split the matrix in two and use the inequalities, and now you just pick u in the smart way. So you pick u, right? You just optimize for u, and the best thing you can do is log to the 1/4 n. And so you get that the expected value of x smaller or equal than you pick up a sigma, and then you pick up another sigma and the log to the 1/4. And here you get exactly the same, right? One of the sigmas goes away with that one, and you get the log to the 1/4, so you get okay, so you get exactly sigma log to the 1/4. Okay, so you recover exactly Seneger's result, and I think now it's completely transparent where the log n to the 1/4 is coming from. Okay, so now just before I finish, let me pose an open problem regarding the Rademacher random variables. So the first question is, well, is this optimal? Is this log to the 1/4 actually needed? And it turns out that it is needed, and there is an example. And this is proven in Sanage's paper, and it's not so hard to prove. And the example is to pick Bij, to pick B to be just a bunch of whole ones matrices here. So when I put this big one, I mean a big one by one, a big matrix made just of ones, and a lot of them, such that the size of each one is k, and there is a total of n entries in this side, in this matrix. Okay. And here it's known that if B is this, it's known the expected norm of x. So if you pick k to be of the order of square root log n, it's known the expected value of the norm of x is of the order of square root log n, while sigma is just square root of k, so sigma is just log n to the 1/4. Okay, so you really need to multiply the log n to the 1/4. And this example, I'm going to use it on Thursday, and I'm going to explain it in a lot more detail. But what's happening, if you think of k growing, when k is 1, there's no log n needed, because this can't get big. But as k grows, essentially what's happening is universality starts kicking in. And so this random variable, made of all the Rademacher random variables, starts looking like a Gaussian and starts having a tail, and this is what shows up here. I mean, very, very intuitively. And so the interesting thing is, okay, this is, we know that if for k small, or at least of this size, then you do need this log n to the 1/4. But there is a result by Sasha Sodin. So this is, in 2009, saying that if instead of having this graph made of clicks, you have a random k-regular graph, so if B corresponds it doesn't matter how small k is, you still have that the expected value of the spectral norm of x is essentially square root k, even for k constant. So what this, in particular for k equals square root log n. So what this means is that while in our instance with Gaussians, especially in the random, in the regular, in the graph setting where everything is super homogeneous, it's completely tight. So sigma and sigma star here completely explain what's happening. This is not true for the Rademacher case. And what I think is an interesting open problem is to understand exactly what are the properties in the graph that make that explain when the log n is, when the extra log n to the 1/4 is there or when it's not. So we know that for a random regular graph it's not there, even for k very small. But if we pick graphs that start looking like this, it is there. And we really don't know what are the properties of the graph that make this that make the distinction between one and the other. Okay, and I'll think I'll stop here, and on Thursday I'll prove this. I'll prove this result as a nice simple proof. Hopefully you'll see how it has applications in several places and explains a lot of known results, and I'll prove it on Thursday.